One of the most famous lines in physics community is perhaps the phrase energy cannot be created nor destroyed. It has paved the way for many answers to scientists' immortal inquiries about the birth and evolution of the universe. More answers in science spawn more questions, however. To think of the universe as a closed system where energy cannot be lost or created anew tempts us to conclude that the same energy that now circulates in space, in the earth, in your body, in the subatomic particles within you, is also the very same energy that existed several thousands of years ago. What then makes the conservation of energy possible? The term conservation implies that the value of a quantity has remained unchanged or constant over time, or before and after certain circumstances. In physics, some quantities like mass and momentum undergo conservation. Another one is energy. The law of conservation of energy states that the total energy of a system neither increases nor decreases. Rather, it only gets changed from one form to another or transferred from one source to another, but its total amount remains the same. You perhaps hear other alternative statements of the law including energy cannot be created nor destroyed, only transformed, and that in a closed system or one that is isolated from its environment, the system's total energy is conserved. Let us review some of the major principles of energy that you have discussed in the past lessons of this course, or even your past science classes. They will be of great importance in helping us establish the mathematical foundations of the law of conservation of energy. First is the conservation of mechanical energy. The conservation of mechanical energy present in an isolated system remains unchanged if there is no friction involved. Once again, there is no friction or non-conservative forces involved. We can remember that the total mechanical energy of the system is equivalent to the sum of the potential and kinetic energies at that particular moment. In equation, we say that E is equal to E plus KE, such that E sub 2 is equal to E sub 1. This can also be expressed in this equation. KE sub 2 plus PE sub 2 is equal to KE sub 1 plus PE sub 1. Take note of this because this is of our first proof of conservation of energy. Mechanical energy remains unchanged without the interference of non-conservative forces, so that E sub 1 at the initial point in time is equal to E sub 2 at any subsequent point in time. From this equation, we can describe the law of conservation of energy as the total mechanical energy of an isolated system remains constant and conserved, provided that only conservative forces are responsible for the work done. Other forms of energy are also conserved, like chemical, thermal, and electrical, and we can group this accordingly as the other energy, which we represent as OE. These types of energy are those which are transformed, transferred, and conserved through the work done by non-conservative forces. Mathematically, we can express this as follows, where KE is kinetic energy, PE is potential energy, W sub NC is work done by non-conservative forces, and OE is other energies. We cannot remove friction in our formulations of the law of conservation of energy though. As we have learned in the previous modules, frictional forces are non-conservative forces, considered as dissipative since they lessen the mechanical energy in the system. To better understand this, let us consider this roller coaster car, which is experiencing a non-conservative friction force while under the influence of gravitational attraction. We can determine from what is called work energy theorem that W done, or the work done by non-conservative forces, is equal to change in kinetic energy and change in potential energy. As the car moves from this point to the next, its work sub NC will be determined by work sub NC is equal to KE sub F minus KE sub I plus PE sub F minus PE sub I. We can remember that kinetic energy's formula is 1/2 mva squared, while potential energy is mgy. Also, work done by non-conservative forces is negative force times distance. Using this individual formula for each individual quantity and substituting them in our previous equation, our equation will be like this. This further explains that the initial mechanical energy of the roller coaster car at that initial point is equal to the sum of its final mechanical energy and the energy transformed into heat energy by friction. And that is another proof of law of conservation of energy. In the next video, let us have some problems relating to this. But that is all for now. I am Gilmar De Castro and see you in the next video.